All right, so for the next one, we're going to look at problems that use conversions across normal, standard, normal distribution as a function of having probability values. So we're always trying to solve for some missing variable in these questions. And I think the first thing we need to remember is that there are three variables that could go into these. So whenever we're talking about going across distributions, we need a mean, we need a standard deviation. We're often going to deal with a score. Now remember, this is either going to be x or z, depending on whether it's normal or standard normal, right? X are raw scores that are normally distributed if it's specified, for example, as in this question. Z is inherently normally distributed because it is the standard normal distribution. So here we have all of these variables that are necessary, and often we also are dealing with a probability, right, or a p-value. And we have to remember that we can use all of these to do any of the calculations we need. So what we need to do first, when we get a problem like this, is put these four things down and fill out, okay, what do I have? Do I have a mean? Do I have a standard deviation? And then you're going to always notice you're trying to solve for something that's missing, one of these four values. So in this question we have here on number 17, it's normally distributed, so we know we can start to use this idea. Here we have a mean of 58 in this question. The standard deviation, it says this normal is, so what is the standard deviation? So this is our question mark. This is what we're trying to solve for. We have a proportion here. 2.5% of the proportion under the curve lies to the right of 61.92. So we have an x score, okay, not a z score, 61.92. We have a p-value, 0.025, right? I just turned that percentage into a proportion. Now, this is the area to the right. It's always important to pay attention. What is your probability? Is it, because it could be the area to the right, it could be the area to the left, it could be the area in between a couple values. Most of the time, again, we're going to deal with either area left or area right, okay? And remember, if you want the area left, then you just need to remember when you're specifying cumulative that you would answer cumulative as true, okay? When you're dealing with area to the right, then you have to realize that you need to do 1 minus, right, the value where you specify cumulative is true. So we'll write examples with that in just a second so you can see how that looks. But these are going to give you those respective areas. So we have to pay attention to what it's asking for. Now, if it's asking for the area between two values, what you're going to do is you're going to use cumulative as true, but you're going to solve for both of those values. And you're going to subtract the smaller, right, value from the larger value. So take the bigger x value and subtract the smaller x value from it, and that'll give you the area between. And we'll talk about that a little more in a second here. So these are what we have. We need to figure out how to get the standard deviation. How can we do this given this information? Well, the easiest way is going to be to use the z-scores, because here's the thing. We can always get a z or a p with only having the other, right? So all I need to know is a p-value, and I can tell you its z-score. And you should remember that we had a couple equations that help us do these things. So for example, x to p, right? We have z to p. We have p to x, and we have p to z. So important to remember that we have these options as far as what Excel is going to do for conversions for us. So in this context, x to p, well, we already have p, we already have x. So we don't need to turn an x score into a p-value because it's already given us both of those pieces of information, right? What we really need to do is get a standard deviation. And the easiest way to figure that out is going to be to realize that I can do that by using the p-value into a z. And so by making a p-value into a z, we have to understand it's going to give us the right side. Now, the thing is, I'm turning it into a z-score, not a p-value. So I would put, 1 in front of the whole thing if I was turning it into a p-value. But here, because you got to remember, the p-value is what the sum of the p-values are going to equal 1. It's the entire area under the curve. So when you're trying to take something away from the 1, you're talking about a probability value. So in this context, you notice the p is inside the parentheses, not outside. So in these ones, you're solving for the p. So in this one, you would do an equation where you subtract the entire equation from 1. But in these ones, what you need to do is subtract the value inside the parentheses from 1, because that's your p-value. So here, because again, I, in this case, want the area to the right, it's going to default to giving me the area to the left. So if I want to flip that side, I have to subtract from 1. So I'm going to do norm invert, right? Norms invert, excuse me. We're going to do norms invert, right, because I'm dealing with z-scores. And so I have a p-value I want to turn into a z-score. The p-value is located here, but I want the area to the right, not the area to the left. So I need to do 1 minus this value. See, because that's going to put only 2.5% in the far right tail. Okay? So once I do that, I get a z-score that is 1.96 if I round to the second decimal place here. So what I need to figure out now is, okay, so that is how far away I am in standard deviations, because these are in standard deviations. So what that means is the distance between my original x-score and my mean has to be this many of the raw standard deviations. So x minus mean, that number has to be this many standard deviations. So this is going to be divided by my z-score. And now I'm going to figure out how many how large the standard deviation for this distribution is. And so you see that this standard deviation is 2. Now let's stop and think about this for a second. It makes sense. If you have 2.5% of the proportion to the right of this value, then this value has to be at basically our 95%, right? Remember, plus or minus 1 standard deviation is 68%, plus or minus 2 is 95%, plus or minus 3 is 99.7, okay? And so it makes sense that we'd get a z-score of basically 2 for the fact where that's located in the distribution. This is the more precise value associated with that as opposed to rounding to 2. But now let's look at this. So the 58 to approximately 62, you see that that basically would be 2 standard deviations away, and that's where it should be located. And in fact, a standard deviation of 2, that is basically 2 standard deviations away, right? 1 standard deviation above 58 would be 60. 2 standard deviations above 58 would be about 62, right? And we are just about 2 standard deviations away. And so that's the type of logic that would be applied. And you would use that same logic then looking at problem like 18, where in 18 here, they give you a normal distribution as a standard deviation. So now we have our standard deviation, okay, is 21. Okay, what is the mean? So what we're trying to solve for is the mean, okay? Now, we need to figure out if we have a score at 175 has 0.0228 probability of occurring. So a score above, so we're dealing with to the right because that's bigger than. So we're dealing with an X score of 175, and we're dealing with an area of 0.0228. Now that area is going to be to the right. So we have to consider that we're going to the right whenever we're going to solve these, because Excel by default wants to give you the areas to the left. So keep that in mind. So keeping that in mind, now we know what we have to solve for. So let's figure out which way we need to take this. Well, we know one of the most convenient ways to do this is going to be to think in terms of the z-table, the standard normal distribution. So we can figure out a z-score for this probability value. Remember, all you ever need is a probability value and you can get a z-score. All you ever need is a z-score and you can get a probability value. Because in those contexts, the mean and the standard deviation are inherently 0 and 1. So they are always known, which means that if you have a z the mean is 0, the standard deviation is 1, you have z, then this is your only possible unknown. If you have a standard normal distribution, the mean is 0, the standard deviation is 1. So if you have a p-value, then only z is unknown. So in this context, we can pretend, for example, that we're using the standard normal where the mean is 0, the standard deviation is 1, right? We have a p-value of 0.0228, and all we need to figure out then is what is our z. And so we could use that z to be able to get our x from our z. So if we use that extra bit, it can help us figure out what all we can do to solve this. So we're going to just pretend, instead of using just normal, that we're using standard normal, right? And find the z-score. It's our only missing value in this context, and then we can translate to the mean. So to find the z-score, we do norms invert, right? And now again, we need area to the right, so we want 1 minus this value, right? So the z-score there is basically 2, right? Just off of 2, okay? And so now we need to figure out how to get the z-score, right? Which we now know is this value, right? How do we get that z-score to be this guy? Well, what we've got to do is find what should be the distance. So if a standard deviation is 1, and we're this many standard deviations away at this score, then this has to be that same distance from the mean. So if we do this standard deviation, right, our normal distribution standard deviation, times the number of standard deviations away this x-score must be, which is what our z-score tells us, we will figure out the distance that this value must be from the mean. So here's our distance. It's about 42 points away from the mean. So then, if we do this value minus this distance, this will take us back to the mean. So the mean of our distribution, rounded to 1 decimal place, is 133. So again, what you really need to understand and take away from this is that we have our equations. We need to think about, if we're doing x to p, we need to remember that we're going to be using norm dist, right? And that's going to take an x value, right, into a p value. And you have to tell it whether or not you want cumulative, right? If you want a z to a p, you need to do norms dist, right? And that's going to take you from a z value to a p value. You see, all you need now is the z value. That's it. Okay? If we need to go from a p to an x, then we want to do equals norm invert. And then it wants your p, your mean, and your standard deviation. Okay? And if you want to, which is what we were doing in this case, go from a p to a z, then we use our norms invert function. So remembering that, we can solve for any of these unknowns, and we can always translate back and forth. Any normal distribution can be standardized. That's that z-score equation we talked about, right? So you can standardize any normal distribution just by doing a score minus the mean, divide that by the standard deviation, right? And that turns, so if you remember, x minus the mean, right, divided by the standard deviation, that turns any raw score into a z-score. Okay, so that's the equation to convert, which means you can convert any normal distribution into a standard normal distribution. And the beauty of that is, when you use a standard normal, you always have mean and standard deviation known. And so then you can use that information to translate back into your typical normal distribution and solve for something that may presently be unknown. And so that's how you would do it for both of those problems and anything that's a similar nature. Make sure you're identifying, which area are we dealing with under the curve, left, right, or between, and what is our unknown value for which we need to be solving.